Hello, everyone. Welcome to the 20th Hintze lecture. My name is Roger Davies and I'm the director of the Hintze Centre for Astrophysical Surveys here in Oxford. And a particular welcome to those of you spread around the globe. We've had over 600 people register for this lecture from across Europe, North America and the Middle East, and as far afield as India and the Philippines. This series of lectures is sponsored by the Hintze Family Charitable Foundation and has been running since 2010. It's attracted some of the leading figures in astrophysics to Oxford. A special welcome to the Hintze family and to all of you who support Oxford physics. This has been a landmark week for Oxford. I want to recognise the outstanding achievement of our colleagues in medical sciences who've worked so diligently to produce an effective vaccine for the COVID-19 virus. This development has given us all an enormous boost. Everyone at the University of Oxford is immensely proud of their achievement. I need to say a few words about the webinar and how it'll work. You will see and hear the lecture, but you cannot ask questions directly. You can, however, type questions into the Q&A facility on your screen. So I encourage you to type in questions as the lecture's going along. We have a team of moderators who will monitor the questions and ask them for you at the end. Of course, I can't guarantee that we'll be able to answer all the questions, but we'll do our best. Now, it's my great pleasure to introduce our 20th Hintze lecturer, Professor Vicky Kaspi. She was an undergraduate at McGill University in Montreal and did her PhD at Princeton, supervised by Joe Taylor, the Nobel Prize-winning astrophysicist. After research positions in Caltech and MIT, in 1999, she took a faculty position at McGill, where she held one of their first Canada research chairs. And in 2006, she was appointed to the Laurent Trottier Professor of Astrophysics. She is one of the world's leading authorities on pulsar astrophysics. She made only the second association after the Crab Nebula between a supernova remnant and a pulsar. The original exploding star that produced the pulsar was recorded by Chinese astronomers in the constellation of Sagittarius in the year 386. She was also one of the discoverers of the fastest rotating pulsar. It spins at 716 times a second. Such a stellar career attracts numerous awards, and Vicky is a fellow of the Canadian Institute for Advanced Research, a fellow of the Royal Society, of the US National Academy of Sciences, of the American Physical Society, and a member of the American Academy of Arts and Sciences. She holds Canada's second highest civilian honor, the Companion of the Order of Canada. She has a long list of prizes, including the Annie J. Cannon Award of the AAS, the Hertzsprung Medal of the Canadian Association of Physicists, the Rutherford Medal of the Royal Society of Canada, and this year, she was awarded the Bakerian Medal of the Royal Society. It's my great privilege to be able to introduce to you Professor Vicky Kaspi to give the 20th Hintze lecture, Fast Radio Bursts.
Hello there, can everybody hear me? Yes, good. Okay, I'm going to share my screen. Hope everybody can see these slides. I'm going to start my slideshow here and just first of all say how honored I am to be the Hintze lecturer and how sorry I am not to be in person at Oxford. I would have absolutely loved to visit, but I'm delighted that so many people from around the globe could attend this lecture. So it's my pleasure to talk to you about fast radio bursts today. You know, when people ask me, Vicky, what are you working on these days? I say, I don't know, actually. And that's because fast radio bursts are currently an astrophysical mystery. We really do not know what their origin is, what's causing them. And I'm going to tell you about this mystery today. And in the process, I hope to share with you some of the ways that science progresses. So you'll see it's a case study in science. There's lots of twists and turns and surprises, head scratching. going on, and I hope both you'll learn about this fascinating phenomenon, but also just about how science is done. So to be sure everybody's on the same page, when I say fast radio bursts, I want to be clear, make sure everybody understands what I mean. And I should also just stop and say that this has captured tremendously the imagination of the public. It's gotten a lot of press because for a variety of reasons we can talk about afterward. But I don't think everybody, always understands what we mean by fast radio bursts. When you hear radio, most of us, or at least of a certain generation, picture a device like this, which has an antenna which collects radio waves, in this case from sources, transmitters that are made by people, not in contrast to radio telescopes that have antennas that will collect them from outer space. But as part of this device, there's a dial where you can tune it so that you're sensitive only to certain radio frequencies. And that involves, tuning into certain radio stations. It would be really bad if you heard all radio stations at the same time. So in the radio, you turn the dial to tune into different radio frequencies. Here, we're at about 100 megahertz or cycles per second, 100 million cycles per second. And the way this works is that a current is produced by the radio waves in the metal antenna, which is then filtered and amplified and sent out to a speaker, in this case, that you can listen to. Now, radio waves are, of course, are just a type of light. And so an antenna, you can think of it as a detector of light, similar to a CCD that's in the camera of your phone or your eyeball for that matter, except in a different part of the full electromagnetic spectrum. This is, you could see the visible portion of the electromagnetic spectrum. That's what we can see, but that's just a really tiny fraction of the different types of light that exist that are distinguished by the wavelength at which the electromagnetic wave is oscillating. So radio waves that I'm talking about here that we use on Earth for communications, but are also used naturally by objects in the sky, stars, galaxies. That sits in the far part where the wavelengths are very, very long wavelengths, tens of centimeters to meters, and frequencies of megahertz or gigahertz. And so fast radio bursts, these are short bursts of radio waves. And when I say short, I mean really short. I mean thousandths of a second, a few milliseconds. These bursts of radio waves last just a few milliseconds, coming from all over the sky. The first one was detected or reported in 2007 using the Parkes radio telescope. And here is the beautiful Parkes telescope in Australia. You can see the size of the aperture here is a 64-meter diameter aperture. It's sitting on top of a 3-story building. It's a very large structure. I spent many years as a PhD student in that building. Today, for fast radio bursts, roughly speaking, 100 have been detected or reported, published. It's a little more than that, maybe 130 or something like that in the literature. But from what we understand, from what we know about radio telescopes, the fact that they see just a small portion on the sky, the way this works is the radio waves come in, they bounce off the parabolic reflector and are focused onto an antenna that's sitting right at the focus. And that can see a small portion of the sky, but from extrapolating the number that we've observed, given how long we've been observing and the fraction of the sky you can actually see at any one time, by extrapolating that, we know that these fast radio bursts is not just an anomaly that happens every now and again. This is something ubiquitous. It's happening an estimated 1,000 times across the full sky every day. So this is something that was a surprise. Nobody expected this, and the origin is unknown. And one thing I can say with certainty is that the origin is not microwave ovens, and you might be wondering why I'm saying that, and I will explain that later. Now, how do we see the radio waves? This is definitely not how we see the radio waves. The radio waves are invisible to our eyes. The way we see, the way we actually detect these things is by taking the output of the antenna and filtering it and amplifying it like a radio does, and then digitizing it, and digitizing it both in time and in frequency. And this is the classic plot. This is actually the discovery plot of the very first fast radio burst. And what's plotted here on the x-axis is only half a second of data, 500 milliseconds of data. But you can see it's broken down. It's been digitized, in this case, something like a millisecond timescale. And on the y-axis is radio frequency. So in this case, we're in the gigahertz range, so wavelength of around 20 centimeters. And this antenna was sensitive across the full range from about 1.2 gigahertz up until about 1.5 gigahertz. And in the case of radio astronomy, we do listen to all the frequencies at the same time, because that's what the stars like and whatever objects up there, including fast radio bursts, like to produce. But you can see here this horizontal line that's at a fixed radio frequency for all time. That is a TV station. So that is a hallmark of something that is man-made, as terrestrial. But the signal, the actual burst, is this bright line that is sweeping through the band. And the sweep is called dispersion. It is the hallmark of a radio wave, of a bunch of radio waves that have traveled a very long distance. And from just looking at this event, looking the way it sweeps, and I'm going to explain what I mean by this, we know that the object has come from a very long distance away. And by very long, I mean from far outside our Milky Way galaxy. In fact, likely from a cosmological distance, that is, from a significant fraction of the distance that across the universe. So now I'm going to have to justify that too. You know, take my word, don't take people's words for things. You have to understand why this dispersion, the fact that the radio waves arrive earlier at high frequency and later at low frequency, are telling us it's coming from cosmological distance. Now hold that thought for a moment. If you correct for that sweep in software, because we believe that the fast radio bursts produce all their radio waves at the same time. And so if in software you add delays to these digitized samples and then sum up across all radio frequencies, then you get what the burst looked like at the source. And that's what we see here in this inset. The radio telescope detects absolutely nothing to begin with. Suddenly there's a broad band, we say across many radio frequencies, burst, and then it goes away and it does not come back. So this is the fast radio burst. This is how we see them. And by the way, this is, it's called the Lorimer Burst, named after the first author of the publication, Duncan Lorimer, a good friend of the discovery of the first fast radio burst. There he is. Now, when I say far outside our Milky Way galaxy, let's also be sure everybody's on the same page. Here's a galaxy. You can be sure this is not the Milky Way galaxy, because it's very hard to take a photo of the outside of your house when you're standing inside of it. This is a galaxy. It's probably similar to the Milky Way, spiral type galaxy, looking down on it. Our solar system is on the outskirts of our Milky Way galaxy. So we are here if this were the Milky Way galaxy. And the point is that the fast radio bursts are not coming from anywhere inside the galaxy, coming from far, far outside the galaxy. So let's just to set the scale and be clear what I mean across the universe. I think everybody's familiar with this planet over here, the Earth. And set in the solar system now, zooming out to a much larger scale, looking back at the solar system, the Earth is now just a little red dot here. It's labeled Earth. The sun is in the center. Now zooming out of the solar system, our sun and our entire solar system forms a part of what we call the interstellar neighborhood, with all the nearest neighbor stars. And of course, on this scale already, our solar system looks like a tiny red dot. And if you zoom out to the scale of the Milky Way galaxy now, the interstellar neighborhood is just a little smudge, tiny little smudge, as I said, on the outskirts. But you can zoom further out. If you zoom further out to the scale of the local galactic group, so our galaxy, like all galaxies, actually, they like people, they like to cluster. We're part of a group of galaxies where here's the Milky Way now, smudge, and here's other nearby galaxies, the Andromeda Galaxy, for example. But our group of galaxies, groups of galaxies also like to cluster, and there's super clusters of galaxies. Here's the Virgo supercluster, of which our local group is just one. And then you can zoom out even further where the Virgo supercluster is just a smudge among many smudges of superclusters of galaxies. And then if you scale out to the largest scale of all, the observable universe, which is largely now homogeneous, and all these little smudges are superclusters of galaxies, and ours is just one. The point is that fast radio bursts come from this final scale here. They're coming from the largest scales in the universe. And that's what I mean by cosmological distances. So that's quite a claim on the basis of just a sweep through a plot, of a digitized plot. So that sweep, I said, I called it dispersion. And what do I mean by dispersion? You're actually quite familiar, everybody's quite familiar with dispersion. The dispersion of light is exactly the phenomenon that you see when you pass white light through a glass prism. The prism spreads out the light into its constituent colors because the light travels differently depending on its frequency or its wavelength in the material. This is the same reason that you see a rainbow. The sunlight hits water droplets that act as tiny little prisms and also spreads out the light because the light gets bent slightly differently depending on its wavelength or its frequency. Now, what these pictures show you is the spreading of the light. What it doesn't tell you that also the different colors of light, different frequencies, travel at different speeds in the material. So that if you were to send in a burst of white light, the different colors would come out at slightly different times. And that's what we mean by dispersion, the time delay as a function of radio frequency. Now you might say, what do you mean by time delay? I thought light travels at the speed of light. Isn't that what Einstein told us? That it's the law that C and E equals mc squared, that's the law. And that's true, but it's only true in a vacuum. So not everybody realizes that C, the speed of light, yes, that is an absolute, but only when it's in a vacuum. When light travels in a material like glass, like water, it doesn't all travel at the speed of light. It travels at a slightly slower depending on its frequency or its wavelength. And space, interstellar and intergalactic space, is not a vacuum. There are free this is the nice, beautiful picture of the center of our galaxy, as seen from New Zealand, in fact. You can see the galaxy is filled with material. And in particular, it's filled with free electrons. So it's not only free electrons, it's certainly filled with atoms that are not ionized, that have not lost electrons, but many free atoms in the universe are ionized and have been stripped of those electrons. And those electrons are key to the dispersing of radio waves as they propagate. And so radio waves that propagate in an ionized medium or plasma, we call that a plasma, get dispersed and arrive at different times. And now you can say, well, what do we know about our galaxy and its free electrons? Well, actually, this is very well understood. So if this were the Milky Way galaxy, and again, it's not, this is a model that shows the distribution of free electrons in our own Milky Way galaxy. It's a model, it's not, it's our best estimate, and it's pretty well calibrated based on galactic radio sources like radio pulsars, which Roger mentioned in the introduction, something I've studied for many years. We know, roughly speaking, the density, the numbers of free electrons throughout the galaxy. And this model here, it's not just a two-dimensional model looking down, it's a three-dimensional model for any direction in the Milky Way galaxy. And so what we've made, what astronomers over the years have made and calibrated pretty well, is a contour plot that shows you lines of constant total, we call it the column depth, or the number of free electrons in a certain direction in arcane units. Don't worry too much about the units here. But in this diagram, the cross here is the center of our galaxy. The Pac-Man over here is our solar system. You can see sketches of the spiral arms. And lines are showing you roughly constant total numbers of free electrons that are gleaned from model, as I said, from pulsar observations or observations of short transient sources inside our galaxy. And so in any direction, if you know what we call the dispersion measure, the dispersion measure, that's the degree of dispersion, the amount of the sweep of a radio signal, you can say about how far away it is. And as I said, it's a three-dimensional model in any direction. If you know the direction you're observing, and you usually do, and you know the amount something has been dispersed, a radio wave has been dispersed, then you can say how far away it is. And in particular, and this is very important, for our model, there's a maximum. Eventually, as you can see here, the galaxy runs out of electrons because the galaxy ends. And so for any direction on the sky, our models robustly predict the maximum number of electrons in any direction, or equivalently, the maximum dispersion any radio wave can have. So so for sources in the galaxy, we determine distance from the measured dispersion, but for sources outside the galaxy, you hit a maximum from our Milky Way. And so here's a cartoon. I'm going to show you a radio source, a fast radio burst, and here's the Earth with a lovely telescope I'm going to tell you about shortly. And we think, and I'm going to play the movie, you see here's our fast radio burst source that produces all the frequencies at the same time, a burst of radio waves, which then travel to Earth, but get dispersed out by free electrons along the path. And so that the shortest wavelengths or highest frequencies arrive first. I'll play it again for you. There's the white light, the burst containing all the colors, but they get spread out as they travel through the interstellar and intergalactic plasma so that different colors arrive at different times. And so that's what this sweep is. The high frequencies are arriving earlier, even though they've also been delayed, but they've arrived earlier than the low frequencies because of the dispersion of radio waves in interstellar and intergalactic plasma. And if your eye is really keen, you can see it's not a linear delay. It's actually a parabolic delay. And for the experts in the audience, this is actually the way the delay goes. It goes as the time delay between two different frequencies goes as 1 over the frequency squared, with the constant in front, this dispersion measure, which is the total number of electrons along the line of sight. So a source that's really nearby is barely dispersed and would come in as a vertical line here. And the Lorimer burst, it had a dispersion measure, and never mind the units, but the maximum expected dispersion measure in this direction was 25 due to our galaxy. Whereas the degree of dispersion, this long delay, this almost half a second delay from the start from the top of the radio band to the bottom, that was over 10 times what our galaxy can produce. The amount of dispersion there is absolutely not explainable by the galactic interstellar medium, the plasma in the galactic interstellar medium. And that is how we knew this source has to be way outside our galaxy. And if it has to be way outside our galaxy and likely at a cosmological distance, because to get all of these, the dispersion measure you need in order to explain the dispersion here is so much larger than our galaxies. You have to, and because the galaxy ends, the intergalactic medium is very tenuous. You have to go a long way to get all of those electrons. That means this source has to be very far away and must be very bright. So this is telling us that these fast radio bursts are huge explosions of some type, producing large bursts of radio waves that we can still detect on Earth. Now, back when these sources were found, some of them that were seen by the Parkes Radio Telescope were quite unusual and had dispersion sweeps that they sort of looked like classic dispersion sweeps, but they were kind of blotchy. The pulses that were produced from them had other anomalies that I don't have time to go into, but there were some strange frequency sweeps and other properties that were kind of puzzling. And yet there were others that were pretty clean. And so it was sort of a puzzle. Are there multiple types of these objects? And then the team at Parkes made an interesting plot. So this is a plot of the number of burst events that they detect as a function of time of day in Australian time, where the light gray sources are the weird ones, the ones that had unusual frequency sweeps and other properties that were strange. And the dark ones are the ones that where the frequency sweeps were nice and clean, but much more similar to dispersion. And this plot looks a little suspicious. And it looks suspicious because so many of them arrive at lunchtime. You know, the cosmos ought not to know when it's lunchtime in Australia. So this was a major clue that something was amiss with these events. And as it turned out, it was due to an errant microwave oven in the visitors' quarters, in the visiting scientists' quarters of the Parkes telescope. So here's the Parkes telescope. The visiting scientists' quarters are down a road. You can't see it. Here's the road, but about 1 kilometer down the road, there's a house where there's a little kitchen. You can prepare your meal when you want to have a snack or whatever. And there's a microwave oven there. And it turns out that that microwave oven, if it was open prematurely while it was still operating, so it had to be running, if somebody was impatient, they were really hungry for their lunch and they opened it, it made a fast radio burst, but only detected when the telescope was roughly pointed in the direction of the visitor center. You know, and I'm telling you this story because that was a bit of a shock to realize. It took a while, and I'm so proud of the Parkes team and of science in general, because in science, we tell it like it is. You know, when something is not as expected, we talk about it. And here's the publication of the realization that some of these initial anomalous looking bursts were not cosmic. In one of the most prestigious research journals there is, the monthly notices of the Royal Astronomical Society, a very prestigious journal. And you can see right here, subsequent tests revealed that they called the anomalous events peritons, can be generated when a microwave oven door is opened prematurely and the telescope is at an appropriate relative angle. So I think this is absolutely amazing. This poor graduate student then, Emily Petrov, stood there, you know, opening the microwave, closing the microwave, opening, closing it, and taking note of all this while somebody in the telescope, you know, this was hard work. And in fact, but it shows how science works. And importantly for the FRB story, the fact that a bunch of them were not distributed at lunchtime, were fully distributed independent of time at all hours of the Australian day, that was convinced the community that this and other distinct observational differences show that the fast radio bursts, the ones that have the normal dispersion sweeps, are excellent candidates for genuine extragalactic transients. Now, so the next question is so once we accept that, yes, these are genuinely cosmic, it's not some sort of strange thing happening at the observatory, you know, what could they be? There's all sorts of ideas. It has to be some huge explosion if it's at a cosmological distance. So some supernova, an exploding star, perhaps colliding objects, colliding neutron stars, a neutron star colliding with a black hole. There's all sorts of ideas. And you know, there's one thing that differentiates them is some would be very young objects, and a supernova tends to be a very young object. Very massive stars don't live very long, so if it explodes, that has to be a star that is not too old. Whereas colliding neutron stars, those are very old systems. So you might expect, well, depending on what it is, you might find them in young type galaxies or old type galaxies. I've highlighted one of the models, which is magnetars. Now, what is a magnetar? Very interesting idea. These are neutron stars that are ultra highly magnetized. I'm going to take a moment. You'll see why later I'm talking about magnetars, even though there's many models for fast radio bursts. But one of the favored ones is that they're magnetars, ultra highly magnetized neutron stars, where the magnetic stresses caused by the enormous magnetic fields, which is upwards of 10 to the 14 or 10 to the 15 Gauss on the surface, that's trillions of times greater than the sun's magnetic field, for example. If you put a magnetar at the distance of the moon, it would wipe out every person's credit card on Earth, by the way, so don't do that. But in any case, the magnetic stresses on these neutron stars caused by the enormous magnetic field we know and observe ubiquitously make massive X-ray and gamma ray bursts. This is a phenomenon that's very well observed. I've actually worked on it for many years. Magnetars have not really been known for large radio bursts though. So this is sort of a puzzle. If you're going to invoke them for fast radio bursts, why do the ones on the other side of the universe produce huge radio bursts when we haven't seen those in our galaxy? We know of about 24 in our own galaxy, and I'm going to come back to this, but we haven't known the ones in our galaxy to produce large radio bursts. So you might think that's not a very good model for a fast radio burst, but there is a lot of energy in those things. They're compact objects, so the millisecond time scale works very well. So that is a possible model. But just coming back to the models, you could at least distinguish these by young objects, like magnetars are very young, versus colliding neutron stars, which are very old. So why not just check and see what kind of galaxy these things come from? And the problem is that radio telescopes do not have very good vision. So you can get great time resolution out of them and detect millisecond type sources, but you can't tell where they come from. So the Parkes radio telescope, its field of view, it cannot distinguish objects within this circle. Its angular resolution, it really is such that this is about 13 arc minutes, or about half the size of the full moon on the sky, where there's 1,000 possible galaxies that FRB could come from. And none of the Parkes sources, at least initially, none of them ever returned. The Lorimer source never came back. So you get one shot at it, and this is all you know is it came from one of these 1,000 galaxies. You can't tell which. And if you go to, say, a larger aperture, the angular resolution improves. So for example, as I'm about to talk about, the Arecibo telescope, one of the largest apertures in the world, 300 meters, it can localize things on the sky a little bit better, but still, there's still many galaxies there. What you really need is what we call an interferometer. That is a combination of many radio telescopes spread apart by great distances. And then, like the very large array in New Mexico, which I will talk about, then you can really localize, and then you can figure out what galaxy it came from, which would be a massive clue to what these things are. So let me come to Arecibo. This is the Arecibo Observatory in Puerto Rico. This is 300 meters across, as I said. This is a 3-story building, a lovely visitor center where if you're in Puerto Rico, you can go in a wonderful museum. You can see the car park out here, lots of truck cars out here. This is a catwalk up to the massive structure, then I think it's 900-ton structure where the antennas sit inside this dome. This is a catwalk you can walk up, and in fact, this is me and 2 of my colleagues, Maura McLaughlin and Paul Ray, at the top of the catwalk. If you zoom in, you can see my knuckles are white. It's scary up there, I'm not gonna lie. But in any case, you might also be familiar with the Arecibo telescope because it was featured in the major motion picture James Bond GoldenEye. In that case, they put it in Cuba. It's not really in Cuba, it's in Puerto Rico. But in any case, this is the first FRB detected by Arecibo. And this was also the first FRB detected by any telescope other than Parkes. And when we found this FRB, we were very excited because I'm sure the Parkes people were getting nervous. No other radio telescopes are seeing these. Maybe they're not real. Maybe they're more microwave objects, but no. At last, Arecibo saw one. We were very excited. You can see the telltale dispersion sweep. Here's the inset. When you correct for the dispersion sweep, you dedisperse it. This one sort of faded away at low frequencies. That was kind of weird. But we weren't too worried about that. But I do have to, unfortunately, inform you, the Arecibo telescope, one of the most powerful telescopes in the world, recently suffered some significant damage due to one of the cables snapping, and you can see the damage to the dish. And unfortunately, it seems like it's going to have to be decommissioned. This all happened just in the last few months. So it's actually a very upsetting time for radio astronomy. So it's a little downside, a little bad news in all of this. But Arecibo did wonderful things for fast radio bursts, and in particular, that first fast radio burst from Arecibo was discovered to repeat. So I told you that the Lorimer burst was never seen again, and none of the Parkes bursts, at least initially, were ever seen again. But we kept looking when we found that source with Arecibo, because Arecibo is so large, it's incredibly sensitive. We thought, well, what if it repeated? Maybe we could detect it. And we looked at it for hours and hours and hours and never detected a repeat burst until one day, suddenly 10 bursts. And here they are. They've now all been de-dispersed so that the dispersion sweep is removed in software so they look like vertical lines. And you can see there's some massively bright bursts from this source. These are all from the same position on the sky at the same dispersion measure. So it's definitely the same source. You can see sometimes they're double peaked. Sometimes they're really bright at the top of the radio band. Sometimes they're really bright at the bottom of the radio band. These two bursts are 6 seconds apart. So the distribution of radio waves and frequency is changing radically. As we say, the spectrum is radically changing, and the brightness of the source changes radically from minute to minute. This was really exciting. It was a PhD student of mine, Paul Schultz, who actually made the discovery. It was very exciting. And really, you know, to his credit, he had looked at lots and lots of data that contained absolutely no signal. It was getting pretty tedious for him, and he stuck with it. So graduate students in the audience, never give up. You know, he made the discovery certainly of the year from not having given up. Now, that was exciting because it repeated, and that immediately ruled out entire classes of model, right? So stars cannot explode 10 times in a minute. Okay, that just doesn't happen a year after they exploded once before. No, no, no. You know, that ruled out any cataclysmic model for FRBs, at least for this source. That was very exciting. But the other thing that this repeating FRB did, it was a gift in a different way. So it ruled out a whole class of models, but it also then allowed us to go to an interferometer because we knew, aha, if you look, you might see it again. So we went, we begged for time at the very large array, this interferometer. This is now an airplane view. So these are large 85-foot, what is that in meters? Oh gosh, I should have checked. I don't know, 30 meters, something like that, dishes in a Y array separated by about 1 kilometer in this particular configuration. If you can detect the source with an interferometer, then you can localize it on the sky well enough to see what kind of galaxy it comes from. Then you can see, does it come from a large spiral galaxy filled with young stars, or does it come from a large elliptical galaxy filled with old stars? You could know. And you can know the distance to the source, because if you know the distance of the galaxy, you can know the distance of the source and confirm. But we observed for 60 hours with the VLA after begging for time, and we did not see any bursts. And so the source was just not cooperating. It was really frustrating. And we went back and said, just give us one more chance, please. And they said, well, okay, last chance. And as we set up during the first hour of setup, after 60 hours of seeing nothing, the source finally cooperated. And for arcane reasons in the interferometer, the way we visualize it, you see this star pattern where they intersect is the source. And that was clearly within these circles, which represent the uncertainty regions from the Arecibo telescope. Clearly, we had pinpointed the location. We knew it was the same source because, and this is hugely, very, very hard to do with an interferometer. This is the team at the VLA was really amazing that enabled this. The same dispersion measure, the same position on the sky, we knew it was the same source and we had pinpointed. And then we could go beg for time at an optical telescope and identify the host galaxy. So this is the 8-meter telescope in Gemini. So this is, you know, science. We keep going. You get one clue, lets you go for another clue, and finally you get to go. So we got 9 bursts in 2016, not just that one burst with the VLA. That gave us a very precise sky position. We could go to the optical telescope and have a look. Oh yes, this was done by postdoc Sriharsh Tendulkar. That's the radio image. And then when we looked with the Gemini telescope, this is the optical image that we saw. And we were expecting some nice big galaxy. And instead we saw this puny little tiny galaxy. It's a dwarf galaxy. And that was just a shock to us. Why is this huge, honking, bright, repeating fast radio burst? Why is it in one of these tiny little galaxies? But the good news was that we could measure the distance of the galaxy, and it was definitely at a cosmological distance. So this was the first time we had actually determined the distance to a fast radio burst. And all the story I told you about fast radio bursts, about dispersion and the amount of dispersion in our galaxy, being way too small to explain it for fast radio bursts. Well, it was all correct. You know, this was all borne out. This galaxy was definitely at a cosmological distance. We got quite a bit of press about this. Here's the New York Times, where the very famous science writer Dennis Overby wrote, "Oh, it's traced to a faraway galaxy, but the caller is probably ordinary physics." I was sort of took issue with that headline. You know, I'd like to bring one of these fast radio bursts to his home late at night and explode it and see how ordinary he finds that. But never mind that. Down the street, New York Post, very different story. We never said they're aliens, just to be clear. We do not think these are aliens. In any case, since that time, there have been 6, and I think actually a few more fast radio burst host galaxy identifications. And this is done by my Australian colleagues using the ASCAP interferometer, which has enough of a field of view that it can detect a few FRBs, not many, but the ones that it can detect, it can localize. And so you can see here in this diagram, these are the different types of galaxies. The white circles are the locations they've determined for their fast radio bursts. In some cases, they can't determine where it is inside the galaxy, but they can determine which galaxy it's associated with. You can see here's one that's in the outskirts of a large spiral galaxy. And in fact, as it turns out, the Arecibo source is the only one so far associated with a dwarf galaxy, with the possible exception of this source here, which is a little far away from its host galaxy. So perhaps it's associated with a tiny dwarf galaxy that's hard to see in this image. In any case, this research done by ASCAP led to a beautiful Nature paper that they published where they plotted the dispersion measure versus the redshift, or rather the distance. And this is the dispersion measure subtracting off the galactic component, the component due to the Milky Way. Because as you go further and further out with greater distance, you expect the dispersion measure to rise due to the plasma in the intergalactic medium. And this is a really beautiful plot, because this black line is what is predicted from cosmology theory and observation that has actually been a component of matter that's long been missing. It's a mystery of called the missing baryon problem or missing matter problem. This is what's been predicted. And you can see if all of the missing matter is actually in tenuous gas between galaxies in the intergalactic medium, well, it's very well explained, but you could see it as long as it's ionized, which we expect it to be. The ionized matter in the intergalactic medium seems to solve this longstanding problem of where's the missing matter. But you can see there's still, this is only 5 sources in their plots. There's still quite a bit of room for discussion about this. And I think basically the value here is that it highlights the importance and potential of fast radio bursts as novel probes of structure in our universe. So not only are these things interesting in their own right, we'd love to know what they are, but even if you never figure out what they are, they'll be wonderful probes of the structure of the universe on its largest scales. But coming back to the fast radio burst problem, never mind their use as tools, which is really wonderful, where did we stand pre-2019? At least one fast radio burst was known to repeat. That was the Arecibo event. And as I said, that ruled out exploding or colliding stars for that source. And it also enabled the first localization of the source, but it left open many, many questions. Do many or all FRBs repeat? Is it just a matter of time before we'll see them all repeat? Or are there different classes, some of which repeat and some of which don't? What is causing the bursting to begin with? And why was that repeater? Is it a coincidence that the repeater was in a tiny galaxy and then ASCAP finds non-repeaters or not? And the only way to answer these questions is to find more fast radio bursts. So, you know, sitting on just a couple dozen of these sources, it's really hard to do, to answer the big questions. And so now I want to turn to this wonderful radio telescope that we've built in Canada called the CHIME telescope, or the Canadian Hydrogen Intensity Mapping Experiment. And that picture you see there might not be like any radio telescope you've ever imagined, but it is a radio telescope. It has a different geometry from the Parkes or other radio telescopes. It's not a parabolic reflector, it's a cylindrical reflector. And in fact, it consists of 4 cylinders. Each is 20 meters across by 100 meters in length. So this is 80 meters by 100 meters. This is located in Penticton, British Columbia, at the site of the Dominion Radio Astrophysical Observatory, which is nestled in mountains, which is really quite useful because it blocks out a lot of the radio interference from the nearby town of Penticton. So having these sitting in a valley is actually quite useful. There's no moving parts to this radio telescope. We cannot steer it physically. It's a transit telescope, so these cylinders are all oriented exactly north-south. And so the sky, as it rotates overhead, because the Earth is turning, we see whatever happens to be overhead. And we see the full northern sky every day. Along the axis of the cylinder are hanging antennas. So each cylinder has 256 antennas hanging on its axis, sensitive in the range 400 to 800 megahertz. And all of these antennas are cabled. This was all done by students and postdocs, brilliant team of students and postdocs, and very few excellent professional staff who cabled this all together. All of those signals are going into a giant, what we call a correlator. It's like a supercomputer that's handling basically 2048 input signals. Half of it, they're sitting under the telescope and also alongside. The input data rate here is 13 terabits a second. That's comparable to the total cellular network of the world, actually, all being analyzed in real time, both to search for fast radio bursts, but also to do a cosmology experiment, which is actually what the telescope was originally designed to do as the titled Canadian Hydrogen Intensity Mapping Experiment. The telescope was conceived of for cosmological purposes to study neutral hydrogen in the distant universe and measure the accelerating expansion of the universe. But it does all of that together with the fast radio bursts at the same time. The cosmology and fast radio bursts are done at the same time. And just for scale, there's our team standing in the axis, a very, very large structure. You could climb up on the stairs there. Now, why a cylinder? So a conventional radio telescope like the Parkes telescope, it sees a tiny region on the sky. And of course, if you have a transient events, most of them don't go in the field of view. You miss them. It's only the very lucky few that happen to hit bang on your target. Most of the sky you just do not see. But if you have a cylinder, it only focuses in one direction, in our case, in the east-west direction. And in the north-south direction, it's a mirror. And so what you're seeing is the full swath of sky overhead. And that is very useful for studying a transient phenomenon where you don't know where the next event is going to happen. You don't know when or where the next event is going to happen. So you compare the fields of view of the CHIME telescope to a conventional radio telescope, and they're orders of magnitude different. And so as the sky rotates, and the transient, the transience events are always there, but you just on average get more of them in your field of view. And that's what makes CHIME such a powerful fast radio burst detector. Now there's a lot of electronics, a lot of software. This is basically a software telescope where, not to get too technical, but here are 4 cylinders and the 13 terabits a second going into this correlator, which is, for the correlator experts, is an FX style correlator made of field programmable gate array chips at the McGill Cosmology Lab run by my colleague Matt Dobbs, and a GPU-based correlator X engine. And all of this feeds into 3 experiments. One is the CHIME FRB experiment that I'm talking to you about today, at the same time as a cosmology experiment. And also we're actually studying galactic radio pulsars also. It's all happening at once. Just to tell you, the F engine is sitting in houses you can't quite see, but they're under the reflectors here and here. And then the X engine sits in these specially designed shipping containers. And the fast radio burst computers, the search computers, is about 128 CPU nodes that are doing the fast radio burst search in real time, are sitting in the shipping container here. So just to make clear though, yes, we see a large swath on the sky. So if you put a single antenna on a cylinder, it sees a huge swath on the sky from north to south, a very large field of view. But if you put many antennas along the axis, then you can combine them in software and effectively point in many different directions at once. And if you also put antennas on all 4 cylinders, you can get directionality in the east-west direction. So each of these spots on the sky is equivalent to one of those Parkes locations. So with the CHIME what the correlator does is it combines the antenna signals and in software forms these beams, these fields of view on the sky all at the same time. So it's like having 1,000 Parkes telescopes all operating at the same time. So it's like searching 1,000 Parkes telescope signals for fast radio bursts all at once. And just really, you know, this is 1,000 now, just to give you the real scale of things. This is clearly, not only is forming the beams a supercomputer problem, but then searching every single one of these digital beams, that's another supercomputer problem. That's all being done on the site in these shipping containers. This is a sketch of the software pipeline for the fast radio burst engine. I don't want to get into too much detail, but the fantastic team of graduate students, undergraduates, postdocs have written this wonderful, wonderful pipeline that now operates in real time in these boxes here. And so this is a view of the CHIME sky. This is how we see the sky in CHIME. This is time now on the x-axis, and this is north-south direction. So we've averaged over the east-west beams, and now we're just looking at different positions on the sky in the north-south. So this is a full sky over many, many hours. And the bright lines that you see are galactic radio pulsars passing through the beam. As the Earth rotates, those pulsars transit through the beam at a fixed location in the north-south direction. These vertical lines that you see here are actually interference. Those are airplanes. Very annoying. We have to get rid of those airplanes. This large arc is one of the brightest galactic pulsars in the sky, which we were very excited at first to see. Wow, we could see it for hours around the transit. That is, even when it's far off transit, we could see it. And that seems exciting until you think about it a little bit and realize, oh gosh, that means this telescope has what we call side lobes, which means it doesn't only see exactly what's overhead. Radio antennas are they're diffraction limited apertures, and you can actually see from angles far away from exactly where your main sensitivity is. And that means that sometimes you can see a fast radio burst even if it's not directly overhead, and that's important. Now, CHIME has turned into a fantastic fast radio burst detector. Here we made the cover of Nature with the clever space and CHIME, haha. Here were our 13 first fast radio bursts. And you can see these have been pre-dedispersed, but we have all sorts of shapes and sizes. And by the way, we detected them all the way down to 400 megahertz, the very bottom of our band. That was the lowest frequency by far ever seen for fast radio bursts. I mentioned the Parkes telescope events were all in the gigahertz range. This phenomenon is clearly present on the sky down to lower radio frequencies. Among our first 13 was the second repeating source. So we're realizing when you view the sky every day over and over again, you see the sources that repeat pretty easily. And this is the second repeating source. This was the lay of the land for fast radio bursts before 2019. These are the different telescopes that were operating, and you can see the different number of sources detected by different radio telescopes. And then CHIME turned on, and this is the same plot, but with the CHIME sources detected. It's kind of I apologize. It's not, in Canada, we're kind of humble people, but it's just so tempting to show this plot. And of course, you realize it ends in 2019, whereas it's been operating throughout 2020, and we have lots more sources. So it's a little bit like drinking from a fire hose in terms of fast radio bursts. We have a lot of sources, and we're now working hard to understand and characterize all of those sources. Till now, we've now discovered 18 new repeaters. Basically, they have some very interesting properties. One of the results that we've already reported is that when you now have a beautiful statistical sample of repeating fast radio burst sources, you can compare their bursts. And we see, oh, did I take out that plot? What we see is they seem to have slightly different morphologies. If you take just repeating bursts and and bursts that are not seen to repeat, the repeaters seem to have bursts that are a little broader in time, last a little longer, a few milliseconds longer on average. So that's curious, and does that support that that the repeaters are a different population or have a different emission mechanism? It's not clear yet, perhaps, but we don't know yet. One of the new results we published just this year is that one of our most active repeater, the repeats come periodically. So this was another shock to us. This is, well, I'm sort of running out of time, so just very quickly, I'll show you this. In this plot, the red triangles are where we detected bursts, and this is date now over many months, and or many weeks. And the gray lines are where the times that we've detected bursts. So they're always, they never appear in the white areas. And these swaths are 16 days apart. So you can see there's some 16-day cycles where we don't see any, and then there's others where we detect many. But the black line is where we have exposure. So that means the telescope is operating all the time when the white is on. Now, of course, the source isn't always in our field of view because the Earth rotates. But there's clearly a periodicity here where the source likes to repeat only every 16 days, and we don't quite know why. 16 days, you say, what is 16 days? What does that seem like? It seems possibly like an orbit. So perhaps this is some sort of neutron star in an orbit that likes to only burst at certain locations in its orbit. I think this is an open question. I don't want to get too into it, and I'm running out of time, so I'll skip that plot. I just want to highlight a very exciting result that was just published in Nature a few weeks ago, where CHIME detected a luminous, a very bright radio burst, and actually two radio bursts, this time from a galactic magnetar. So I mentioned to you earlier that one of the leading models for fast radio bursts is that there are these ultra-magnetized young neutron stars called magnetars, those things that are known and have been observed ubiquitously to explode in X-rays and gamma rays due to instabilities in their magnetic field, but have not been known to produce giant bursts of radio waves. Well, we found one. The source is called 1935 plus 2154, if you must know, and it produced these two giant bursts of radio waves at the same time. This is X-ray data. The radio bursts you can see here these are when the CHIME bursts went off. They're almost exactly coincident with two giant X-ray bursts from this magnetar. And so that's very exciting. And this was also, by the way, detected by a different type of radio telescope called the STARE-2 telescope that's built by the University California Institute of Technology. They have a much less sensitive instrument. They only detected one of the two bursts, but they were operating at a frequency of 1.4 gigahertz. So they're at a slightly different frequency. We're at a lower frequency, 400 to 800 megahertz, but they could still see one of these bursts, and that was very nice when they were able to confirm our detection. And so that says, wow, one of the magnetars in our galaxy can produce giant radio bursts. Does that mean that fast radio bursts are magnetars? And so the answer is maybe. I don't think we're certain, but this plot, this is a plot that shows distance of sources on the x-axis, where the galactic radio pulsars are all fairly close by, so at low small distance, and the fast radio bursts are a pretty large distance. So this is many, many orders of magnitude in distance. And this is how bright the burst is. So this is telling us how bright the source is. Now, of course, how bright you observe something is not necessarily the same as how bright it is intrinsically. We call, the source, if something's really nearby, it could be really bright, but intrinsically very dim. Whereas if something's very far away, it could be fairly faint, but still intrinsically very luminous. So these are lines of constant energy output. And so that's what you really want to compare, is the amount of energy a source produces. And what you can see is that the galactic radio pulsars energetically, yes, they produce radio bursts, which is great, because that allows us to calibrate our free electron model in the Milky Way galaxy that I told you about earlier. but they're very low energy. The energies are not very large. Whereas this new galactic magnetar, it sits at an energy here of about 10 to the 35 ergs. And that is now comparable to the energies emitted by the closest, least luminous fast radio burst sources. So these are the uncertainties on the distances for some of the closest, lowest energy fast radio burst sources. And you can see that the energy of the galactic source that we just detected is comparable at the lowest end to the least luminous fast radio burst sources. So if you had put the local source, the galactic magnetar, at the distance of a nearby galaxy, yes, we would have detected it as a fast radio burst, absolutely. But can it explain all fast radio bursts? Well, some of them are still 1,000,000 times more energetic. So can it explain low luminosity fast radio bursts? Probably. It's looking very promising. Does it explain all fast radio bursts? That, I think, there's still room to wonder. So just to wrap things up, coming soon from the CHIME Fast Radio Burst Project, soon we will be putting out a catalog of our first 538 sources with an in-depth statistical analysis of their property distributions, sky distribution. And also, we hope in the coming year in 2021 to be putting out public alerts. We are working on that system so that we can tell the world instantly, or maybe not instantly, but certainly within a minute and maybe even faster, when we've detected a fast radio burst, so other people can go and try and correlate with other events going on in the sky. And also, in the next couple of years, we plan to build outrigger telescopes to CHIME, that is mini versions of the CHIME telescope at many thousand-kilometer distances from CHIME itself, so that we could do this interferometry trick and determine positions that are sufficiently accurate that we can detect host galaxies for every CHIME event. And so we plan to be building them, one in the Algonquin Park, hopefully in Canada, one at the Green Bank Observatory in the United States, another one about 100 kilometers away from CHIME itself. And so that's it. And I just leave you with a team photo and my tremendous gratitude to our funding agencies and to the fantastic team that I represent of students, postdocs, my colleagues, and professional staff, just amazing people that have made this work. And I encourage you to stay tuned. There's lots more results to come out of CHIME, and I will leave you with this beautiful drone video of CHIME. So thank you very much for your attention. I apologize. I see I went a little bit long, so perhaps I'll stop sharing my screen. But you can see this drone video on our website.
Thank you so much, Vicky. What a tremendous canter through a very exciting topic, which we seem to have captured at exactly the right moment where it's all happening, and it's that you got across the excitement of discovery and the way science works so crisply. So it's wonderful having so many people because that's what we can do online. The part that's missing, of course, is the huge thunder of applause that would normally come at this point. So I can't thank you enough. That was wonderful. We very much look forward to you visiting Oxford in person when everybody gets vaccinated. Having said that, we have a team of our question moderators all set to go, and so I'm going to hand over to them. There's a plethora of questions already lined up, so over to you, Lucy.
Hi, Vicky. Thank you for an excellent talk. So as Roger said, there's been lots of really interesting questions, and I've tried to combine a few together to ask you a few things about radio telescopes. So first, thinking about the discovery of FRBs and sort of early in 2007, is there a simple reason why FRBs weren't discovered before 2007, given that there were radio telescopes then? And then in terms of nowadays and the advent of CHIME and everything, if cylindrical radio telescopes have a relatively large sweep area, why are parabolic telescopes more prevalent? And does that mean that parabolic telescopes like Arecibo are now obsolete?
Ah, yes. Okay, well, to answer the first question, it's all about technology. It's all about computer speeds. In the end, this is fueled a lot by, people's interest in gaming. Not only gaming, I'm sort of joking, but just computer speeds, the ability to collect, write data out really fast and then process it really fast. So the reason that the fast radio burst community is so comprised of people who used to study radio pulsars is because we had all the software tools, but it was slow going. And so we would search for single pulses, but only to a maximum dispersion measure that we expected for our galaxy. So for many years, we certainly didn't have access to the millisecond time scale. And then when computers got faster, we could start looking at really short things, and we found very fast radio pulsars as well. But then even though our computations were so limited that we had to be parsimonious, and we didn't think to look out beyond. And so, the Parkes team, a little bit it was serendipitous. They were looking toward the Small Magellanic Cloud. So they were looking at higher dispersion measures than you might otherwise expect due to our galaxy. And that's how it came to be. So it's really computer driven. Now, your second question, yeah, so it really depends on what your science focus, what your science goal is. So the cylindrical apertures are fantastic for large fields of view for doing rapid surveying. But as you see, they're not so good for localizing. So our colleagues at the ASCAP telescope who are using, parabolic reflectors, they can localize instantly. And moreover, if let's say you want to image the sky, and that's a vast area of radio astronomy, making images of galaxies, and you want a nice simple beam. You want to understand your side lobes really, really well. And so a cylindrical telescope is just more complicated. The symmetry is broken, and it's a more complicated task, and particularly a transit telescope where you can't steer it to look at a point source as it transits, and you don't have a choice. You can only take what you get up in the sky at any one time. So it has advantages, but it also has disadvantages, and I don't think that'll put the parabolic reflector business people out of business at all. No.
Brilliant, thank you very much. I'm going to hand over to Bettina now for the next question.
Hey, Vicky, this was a very nice talk, and there was a lot of appreciation in the question board for your nice presentation. So I combine actually several questions regarding the frequency range of FRBs. So there was the question, what is the total frequency range of all these FRBs which are reported to have been seen with different telescopes? And is there a maximum frequency until which FRBs are seen? And what does the frequency range tell us about the source object?
Right. So the original Arecibo repeater has been seen up to, I think, 8 gigahertz. So pretty high. That's fairly high in radio frequency. We have now also seen bursts down to 300 megahertz using the Green Bank telescope in West Virginia, and also a telescope in Italy and in India, the GMRT has detected them at low frequency. At low frequency, what it tells us is, when you have a very dense medium, where there's a lot of material around, it's hard for low frequency radio waves to escape. And so the fact that you could see them at low frequency tells you that the medium in which the source is embedded cannot be too dense. So it's a constraint on the local environment of the fast radio bursts. Also, it's a constraint, I didn't talk about this, but radio waves get scattered. I talked about, the total number of free electrons, or we say the column depth of free electrons. I didn't talk about how they're distributed. They could be clumpy. They don't have to be distributed perfectly uniformly. Now, for the dispersion measure, that doesn't matter, but if they're clumpy, that can scatter the radio waves. And that is a strongly frequency dependent effect. So if you can, and it's huge, much larger at low radio frequency. So if you detect them at low radio frequency, then you know immediately they couldn't have been too much scattering, so that the density around them, at least the ionized component of the free electrons, it had to be fairly uniform. It couldn't be too scattered. So those are the sorts of things we learned from the frequency extent of fast radio bursts.
Okay, thank you very much. I will now hand over to Aris.
You have to forgive me that even though it's midday here in Montreal, the latitude's such that the sun is sort of low in the sky and it's just shining in at weird angles in my window. So sorry if I look weird.
It's fine. Thanks a lot for all of that, Vicky. It was really, really very, very interesting. I'm also going to combine a couple of questions about the dispersion measure. So the questions are, how do you measure the galactic electron density? And then how do you know that you can construct an electron density map spread across the universe in order to estimate distances and so on up to the distance of FRBs? And finally, when you detect an FRB, how can you be sure that the FRB is coming from the galaxy that you've localized it in and not simply passing through that galaxy and coming from a galaxy beyond it?
Yeah, no, great questions. Okay, yeah, all great questions. So the dispersion measure, and I know, Aris, you could also answer this question, so I'll do it, but basically we have galactic radio pulsars that produce regular pulsations and are dispersed. And for many of those pulsars in our galaxy, so we measure the dispersion measure directly, but we also have independent distance estimates. So some radio pulsars, for example, are located in supernova remnants, where we know the distance. Or some radio pulsars have a binary companion for which we can have an independent distance estimate. Or some are in globular clusters where we have an independent distance estimate. And there's enough of these that, given the known distance and the dispersion measure that you get directly, that you can calibrate out the distribution. Now, are there uncertainties in the model? Absolutely. But different teams, independent teams, there's actually three different independent attempts to do this, to put all this information together, and they agree pretty well. So I think we feel pretty confident about that. Now, the intergalactic medium is another matter. And measuring the intergalactic dispersion measures, that is, now you're on the forefront, because for many years, as I mentioned earlier, you could have an entire cosmology talk where you talk about the missing baryon problem, that is the problem of the missing matter, where we know what fraction of the total energy density of the universe should be in regular matter. And yet when you look at all the stars and all the galaxies, you don't see that much. So the hypothesis has always been that there has been matter between the galaxies, or even in halos of galaxies surrounding them. And so when you measure the fast radio burst dispersion measure, you can subtract off the galactic component, and then the rest is a combination, is a sum of whatever's in the intergalactic medium between you and the source, and whatever's in the host galaxy of the FRB. So the FRB is in a galaxy itself, which has its own interstellar medium, just like the Milky Way, and that contributes a dispersion measure. So that actually is a problem. And the question is, so if you measure just one galaxy, you don't know what fraction is from the intergalactic medium and what fraction is from the host. But that's why that Macquart et al., that plot that I showed you from the multiple localizations, is so important. Because what you saw is that if you subtract off just the Milky Way component, the remainder of the dispersion measure is proportional to distance, which says that the host galaxy contributions on average, not always, but on average, are relatively small compared to the intergalactic contribution. So this is how you're learning about the structure. Now, there was a third question that you asked. Oh, yeah. So if you localize it and it kind of seems to be coming from a galaxy, how do you know it's really related to that galaxy? It's a great question. Great question. So the answer is statistics. So we know people have counted galaxies, people who, well, you're an Institute of Astronomical Surveys, did I understand that correct? So people surveyed the universe for galaxies. So they know the distribution of galaxies and the number density of galaxies on the sky as a function of how bright the galaxy is or the type of galaxy. And so you can ask, well, perhaps they're just chance aligned, but what is the probability of that? How common are galaxies that you would just happen to have a chance alignment? So you can do the statistics. And then you see that these localizations are all statistically incredibly improbable just by chance. So that's what we rely on to assert that there's an association.
Thanks, that's all very clear. I'll hand back to Lucy for one final question then.
If Lucy's speaking, I cannot hear
Hi,
her.
Vicky. Okay. So we do have time for. Can you hear me now? I think my internet briefly froze.
Yes, now I hear you.
Fantastic. Well, we have time for one last question. So this is sort of building on what you've been talking about already, but would you be able to explain a bit more what you mean by using FRBs as novel probes in relation to large cosmic structure? So both in terms of how they're novel and also what characteristics exactly you're able to probe.
Yes. So how are they novel? So they're novel because, you know, we've had other cosmic probes in the sense of objects that you can see from great distances. But what the fast radio bursts have is imprinted on their emission records of where they've been and what they've gone through. So this scattering property that I mentioned, and I didn't show in the talk, I'd love to show it to you, but the pulses get broadened in a very specific way by scattering, and that is a record of what it is traversed through. Similarly, the dispersion measure is just such a record, and there's other records as well that I didn't mention, other fossils in it. So when you look at that, you know, the spectrum, we see what we call scintillation, twinkling of the radio waves effectively as a function of radio frequency. All of these things together are imprints and records of that line of sight, of that one little pencil beam in that one direction. Now, if you get thousands of these pencil beams in all sorts of directions, you are seeing the intergalactic medium through which they've passed. Yes, with some record of the host galaxy, which could be a little bit of a problem. But we think for various reasons, as you go further and further, that's less and less of a problem. And that just has to do with the way the universe expands. It matters less what the host contribution is as you go further out. What was your second question? Oh yeah, yes, no, so about structure, that's right. So this missing baryon problem, where are all these baryons? Where is this missing matter? It could just be in a uniform tenuous medium throughout the intergalactic medium between galaxies. Or it could be that every galaxy has its own halo of unseen, and this is not dark matter. So dark matter is a separate problem. Yeah, we're not dealing with this. We don't answer the dark matter problem here. We're answering the normal matter that is just hard to see problem. And so it's hypothesized that some of these missing baryons, this missing matter could be in halos of galaxies as well. And so the fraction that's in the halo versus the fraction that's in the intergalactic medium is these are important for understanding galaxy evolution and how structure formed. Because you can test models of structure formation. You know, the universe started out as this primordial soup, and quantum fluctuations in the primordial soup eventually led to gravitational collapse and the formation of galaxies as the universe expanded. But in detailed computer simulations of all of the structure formation, you can then see, oh, do the galaxies end up with these halos of baryonic matter? And so some of them do, some of them don't. Well, you can then constrain these models and test them with fast radio bursts because they can now probe this otherwise unseeable material.
Fantastic. Thank you very much. I know I would happily go on asking questions forever, but I will hand back over to Roger now.
Thank you very much, Lucy. And thank you very much to the moderators for a terrific job at handling the over 50 questions that came in. So some of them were averaged over to produce the questions that were actually asked. Thank you to all the people who put in questions. That's terrific. And thank you to the moderators as well. A great job. And what, not quite finally, so the other person I want to thank is our IT team. Without them, these kinds of events would be impossible. So thanks to you guys, that's terrific. Vicky, you've done a tremendous job for us here. I'm sure everybody's excited to hear about the next steps in this puzzle. We're right at the cusp of some exciting discoveries. You've given us all the background and given us a taste of what those discoveries might be. I'm sure we'll all be looking out for that in the new year. Talking of which, we will have another Hintze lecture in about 6 months' time. At this time, I don't really know whether that will be an in-person lecture or whether it'll be another one on the internet, but either way, I can assure you it'll be an exciting lecture. So with many thanks to Vicky again from the over 300 people who were listening the whole time. Thank you so much indeed, Vicky.
It's a great pleasure and honor. Thank you for listening.
Thank you.